Neon lights may bring you delight, but there's probably not neon in those lights anymore. Instead, there's probably something like argon. So today we're gonna talk about noble gases, neon, and fluorescent lights. And so let's dive in.
So start with a quick overview and then I'll back up and go through the details. So basically what we're going to see is that neon, like all other elements, it's made up of units called atoms. These atoms are made up of smaller parts. We have protons, neutrons, and electrons. And those electrons are going to be excitable. And so what can happen is that if you provide these atoms with energy, those electrons can get energized. And so sometimes what they can do is they can get energized to just like a higher energy level. So they're still hanging out in that atom. They're just a little farther away. They're a little more excited. But they can't stay in that excited state for long. And so then they fall back down. And when they fall back down, they have to give back the energy that excited them, and they do this by giving off light, and we call this luminescence. So this is where we're going to get the red light from a neon, is this luminescence that's coming from those electrons being excited and then falling back down. Um, but what can happen is if you give these atoms even more energy, then the electrons can get so excited that they actually kind of come away from the atom, and then you're left with an imbalance of protons and electrons. You've lost this negatively charged electron, and so now you're left with a positively charged molecule. And these are traveling through. So you have and this is happening when this happens in a gas, we call this a plasma, so it's charged gas. And so what we can do is we can fill a tube with neon. And what's great about neon, as I'll get into, is it's a noble gas. So basically, it's typically really inert or non-reactive. But it can do these things like get excited and luminesce, or get excited and ionize. But when you're not touching it, it's not going to like go exploding or anything. So it's really stable. And then we could provide energy by adding electricity. Well, now what we're going to do is we're going to be allowing it to ionize. So we're going to be making those charged molecules. And those charged molecules, well, they're going to travel through this tube to the different electrodes. And so we have a positively charged end, and the electrons, the free electrons, are going to be wanting to go there. And then we have a negatively charged edge, and those positively charged neon ions are going to want to go there. And what you're happening is that this is happening in the gas in this tube. And so these gas molecules are like whizzing through the tube trying to get to their opposite charge, because opposite charges attract. And so when it's doing this, it's going to be bumping into neon molecules along the way. And when it bumps into those neon molecules along the way, maybe it doesn't provide enough energy to actually ionize them, but it might provide enough energy to excite them temporarily, and excite them in the way that then they can't like go all the way out, but they get excited for a while, then they fall back down and they give off light. So you're able to, from this neon that's normally just like hanging out and inert and not going to do anything, you add the electricity, you get this to ionize, you make this plasma, this charged gas. Those gas molecules are going to go whizzing through the tube, bumping into other neon molecules. End result is you have these neon molecules, the electrons get excited. You can't stay excited forever, so they fall back down and they give off this light. And different elements can do this. But and so but different elements will have different lights that they give, color lights that they give off. So it's not that neon is like the only thing that can do this, but neon's great in that it's inert because it's one of those noble gases. You don't have to worry about like things reacting inside of the tube. And with neon, you can get this like reddish light, but maybe that's not what you want. There are other different noble gases that you can use for this. So these would also be inert or non-reactive. And so often what you see is argon used. And so with argon, you're going to get like a purplish light. We'll talk more about why argon later, but basically it's easier to ionize. Its electrons are farther away from the protons and that are holding them in. So it's going to be easier to ionize, easier to excite and things like this. And so argon's often used. But then you're going to get this purpley light, right? Well, it turns out you can make a mixture of these different noble gases in order to get different colors. But even still, you're going to be restricted to the colors that you can get by mixing those. Instead, what's often done these days is that the lining of these tubes is going to be painted. So you could just paint it with like a plain color. So say if you painted your tubes blue and then you have this red light from the neon, you could get like a purpley light. But maybe you want some other color that you can't get from this mixture, from just like mixing different noble gases or using like one of these noble gases. And so turns out you can get a lot more different colors if you actually have it so that instead of the light that you see coming from the luminescence of those like noble gas molecules, instead you have it come from fluorescent molecules, or like what we call phosphors, coated onto the walls of these tubes. In this case, what happens is we kind of get a chain reaction where the light that's given off from this noble gas is actually going to be used to excite the molecules in the phosphor molecules. And now we get a kind of luminescence, so a kind of light that's being given off that's we call fluorescence. And so luminescence is basically where an electron gets excited and then it falls back down. And there are different types of luminescence that depending on where that energy is coming from that's exciting that electron. And so in the case of fluorescence, that excitation energy is coming from absorbing light from some other process. And so this light is going to be like little packets of energy traveling in waves. And when another molecule absorbs that light, then those electrons can get excited in the second molecule, fall back down and give off light of a different wavelength. And so we can end up getting different wavelengths of light. We can get different colors by having different fluorescent molecules on the walls of the tube. And because now we're relying on the color of that second molecule and not the color of the first molecule, well, we don't need to use neon. And so often, because argon is like simpler and easier to ionize and easier to energize and things like this, argon is often used. So a lot of the so-called neon lights will actually have argon. And here we're actually talking about kind of like fluorescent lights, because the light that you see is actually going to be coming from that fluorescence. And often these days, we have fluorescent lights these days often use like argon and mercury. So it turns out that mercury, it's going to be able, when it luminesces, it gives off UV light. And this UV light is really, really handy for reacting with different phosphors that you have in the tube. And so you can have like argon kind of serve as filler gas. And so it's going to basically allow there to be like stuff in the tube that's not going to be reacting. And it's also going to be still able to ionize. So you're able to form that plasma. So you're able to connect that like circuit and stuff and keep this electricity flowing in the tube using the argon. And then the mercury, this is going to help provide those like the energy and stuff to excite the mercury. And so here the mercury then is going to be luminescing, and it's going to be luminescing then giving off light that's going to excite the phosphor in the tube, and therefore you'll get the color. But this is why so mercury turns out to be really good and efficient for this and things, and you get that UV light that can excite the phosphor. But then you have to deal with mercury. And so that's why you have to like take care when you're recycling these light bulbs and disposing of the fluorescent light bulbs. These days, like LEDs and things like that are often used a lot more, but your typical like fluorescent light will typically contain argon and mercury. So now let's go back to the beginning and talk about all of this in more detail, because I love details. Okay, so what we're talking about, we're dealing with noble gases. And so what's a noble gas? It's one of these elements that you'll find on the far right of this periodic table. And so basically all the atoms are going to want to be like the noble gases. And the reason why all of these atoms of all these other elements are going to want to be like the noble gases is because these noble gases have a full outer shell of electrons. So going back to this idea of these subatomic particles, so we have the protons, the neutrons, and the electrons. And so the protons are positively charged, and they're going to be held together in this tightly this dense core called the nucleus. They're kind of held glued together by these neutral molecules called neutrons. And then these electrons are kind of whizzing all around. And we can never predict exactly where these electrons are going to be, but we can kind of their places where they like to hang out more, like orbitals and stuff. And we can simplify things by drawing a shell model where we basically represent these different shells of electrons. It's not really this simple, but basically you can think of like each time you go down a row in the periodic table, you're adding on a shell of electrons. But when you go within a column, what happens is that you're actually keeping steady the number of valence electrons. And so valence electrons are the electrons on the outer shell of like the outermost shell. And why this matters, why we care about these valence electrons so much, is that they're going to be the most reactive because they're farthest from the pole of the protons. So electrons are negatively charged, protons are positively charged. The positive charge of the protons is going to help rein in these electrons. And the farther away the electrons are from that positive charge, the easier they're going to be to come off and to react and things like this. And this is why we'll see that argon is going to be easier to ionize and excite than when we have neon. But in the case of all of these, even if you have like in one of the lower shells, basically all of the atoms are going to want to make it so that they have a full outer shell. And so these atoms are basically filling in their shells of electrons from the inside out. And so you have to fill one shell in order to get to the other shell. But atoms want to have a full shell because this is going to make them the most happy. So atoms of other elements that aren't in this noble gas category, well, basically they're missing electrons to make it to that full outer shell. And so they can get those electrons by like giving or taking electrons, in which case they would become ions, they become charged molecules, or they could share electrons in covalent bonds. And this is how we get molecules form. But with the noble gases, they already have everything. And so this is why we consider them like inert or non-reactive, is because basically they have what they need. They don't need to form bonds with other molecules in order to do things, or in order to be happy. But this doesn't mean that they can't do anything. And so as we talk about, like they can do these things, like those electrons can still get excited. And they can get excited and fall back down, in which case we get this luminescence, this light given off, or they can get ionized. They can get excited all the way out of their orbit, in which case we get a plasma. So we get this charged gas. So this luminescence is going to be what we see as the colored light, at least originally, in like traditional, like old school neon lights or whatever, that red that you see, that's coming from this luminescence from the neon. And you would get like a purple if you were to look at argon, or you'd get, basically like a bluish if you look at xenon. So basically you can see that all these different gases are able to do this luminescence, but you're getting different wavelengths of light. You're getting different colors that you see. So different colors are corresponding to different wavelengths of light. And different wavelengths of light are corresponding to different energies. So light is just like light we can see, light that we can't see. It's all made up of these little packets of energy called photons, and these are traveling in waves. And all light travels the same speed, the speed of light, but these photons have different energy levels in different atoms. And so if you have more energy, basically you'll go up and down more times in the same amount of space. So we say that you have a shorter wavelength. And if you were to look at like how many times the wave would hit a wall in a certain time, if that wall was like, it was going up and down through the thingamabob, like how many peaks would it hit? And so that would be the frequency. And so we would have a higher frequency, higher energy, shorter wavelength. So basically think about those different colors of light as corresponding to different energies. And this energy is going to be different for these different molecules, because that energy, well, what's it corresponding to? It's corresponding to the energy that's given back off by these molecules, by those electrons, when they're falling back down from their excited state. And the excited states, the difference between like a non-excited state, so the ground state, and an excited state, this is going to be different for different atoms, for different molecules, different elements. And so I like to think of it kind of like an electronic floor plan where you have these different, like an apartment, we call this like a Jablonski diagram, but basically there are different energy states that an electron can have. And it can't live in between those states. So it can go from like one floor to the next. It can go from one energy level to another energy level to like from a ground state to an excited state, but it can't hang out in between. You can be on the different floors, but you can't be hanging out like suspended in the air between these floors. You can also, there's kind of like some wiggle room in the absorptions and emission and stuff, because you can kind of like, just like you can be standing on your bed, they can be like vibrational states and stuff within these different excited states, these vibrational levels. That's why you don't get like just one thing that can be absorbed or one thing that can be given off. It's kind of like a curve if you were to look at the absorption and emission. But anyway, so basically though, the distance between these different floors is going to be different for different atoms, for different elements. And so, and this difference, it matters because the distance is going to be what's given back off when those electrons fall back down. And so because all these elements have different like electronic floor plans, they have different energies between those different amounts of energy that are going to be absorbed and going to be given back off. They're going to give off different colors of light. And so this is why you're going to get different colors of light from these different gases. And if that's not good enough for you, then what you can do is you can add a second layer where we're actually dealing with fluorescence. So luminescence is the overall term for when the electrons get excited and they fall back down. But that exciting energy can come from all sorts of different sources. If it comes from a chemical reaction, we call it chemiluminescence. If it comes from light, we call it fluorescence. So remember, we were just talking about like how light is energy. So those little packets of energy. And so if the packets of energy have exactly the right amount of energy to excite you from one floor of that apartment to another floor, well, then this molecule can actually absorb it. So when we talk about a fluorescent molecule, so in this case, we're like calling this like phosphors that are coating the tube. You have basically, it's going to have an absorption wavelength. So it's going to have like one wavelength, one energy that's going to excite it. And then it's going to give back that energy. And so it's going to give back that energy in the form of other light. And note that there's like other ways, like not all of this energy is going to be directly converted back into that light. So typically you see a slightly different wavelength than the wavelength that you absorb. So you can have fluorophores be absorbing, like giving off quite different colored lights than they're actually absorbing. There's all sorts of different like tricks and stuff that you could use to have molecules that'll give off different colors. The bottom line is that you can get a bunch of different colors, even it doesn't have to necessarily correspond that closely to the absorbance of the photon that you're actually absorbing. The color of the light that's given off, so this is the wavelength of the light, it's basically going to be restricted based on the input. And so when you absorb the energy, you have to give back that energy. But when you absorb the energy, you're not getting more than you absorb. And so you typically can't give off a higher frequency of light than you absorb. And so if we go back to looking at our electromagnetic spectrum, what we're dealing with neon was something like reddish, and that's at the very bottom of our visible light spectrum. So there's not a lot of places you can go from there in terms of getting other colors. So if you have argon and stuff, you're at a higher energy, and so this is going to be more options. When it comes to mercury, you're all the way in the ultraviolet. So you can have access to the entire visible light spectrum if you have the right phosphors. And so if you combine all the colors of visible light, you get white light. And so with mercury, you're actually able to excite a bunch of different fluorophores to give you different all the light colors that can combine to give you like white light. And so you can get fluorescent lights that look white, as well as getting like different colors. And this is taking advantage of that high energy light that you're getting from the mercury. But you wouldn't want a tube of just like full of mercury and stuff. And so this is where the argon comes in typically to act as the source that can ionize, that can form this plasma. The electrons flowing through this tube that are going to excite, the bang into those mercury molecules, and allow the mercury to give off that UV light. And then that UV light can be converted into visible light colors from the phosphors on the tube, absorbing the light from the mercury light and then giving it back as light of a different color. And so this is going to allow you to make, you can have like all sorts of different colored lights. I should mention that like this is not my field of expertise. I'm a biochemist, so I'm used to dealing more with things on the periodic table, more like carbon, nitrogen, oxygen, hydrogen. But the basic principles of what these atoms are made up of and things like that are the same. And so hopefully I haven't misrepresented anything. And if you find any mistakes or anything, please do let me know. I'm always eager to learn. And this is my understanding of how this process works. And so to review, we have these noble gas molecules like neon, which are going to be really boring on their own, which makes them great if we don't want something reactive. If we want just like a tube of gas we can have hanging out. But that tube of gas isn't going to be doing much of anything, which is why, well, we used it in the first place. But we wanted to actually do something when, well, we wanted to do something. And so when we add electricity, we can get the furthermost electrons, some of these like valence electrons, to actually pop out of the atoms of these noble gases. So they can't do much. They're not like forming bonds to other molecules, but they can get ionized and they can luminesce. So basically when they ionize, that electron pops all the way out. When you're losing that electron, you're left with a positively charged molecule and a negatively charged molecule. So we call charged molecules ions. And these ions are going to travel through the tube to find their oppositely charged side of the tube. And in doing so, they're banging into all sorts of other molecules along the way, other neon molecules or other molecules that were in the tube. This is going to be exciting the molecules, and maybe not exciting those electrons all the way out of their orbit, all the way away from the atom, but they can excite them a little to an excited state. But then those electrons can't stay in that excited state, and they're not like far enough away from that atom that they can just like fly away. So the protons pull them back in, and you give back the energy that you absorbed because you have this preservation of energy. And so the energy is given back off, and this energy that's given back off is given off in the form of light. And so we call this luminescence, and this is why we see a reddish light with neon and a bluish or purplish light with like argon and stuff. We can mix different noble gases to get different colors, or we can actually paint the walls of the tube. If we put a fluorescent molecule on them, like a phosphor, then what this fluorescent molecule can do is you can get a chain reaction where the luminescence from those original excited atom electrons are exciting the electrons in this paint, and then those are going to be giving off a different light. And so this is allowing us to kind of access more different light colors than we could in the case of just relying on the natural emission of that element. Often, instead of neon, argon is used. It's going to be easier to excite and energize. And it's also going to give us a higher frequency of light that it's giving off. And therefore, it's going to allow us to excite fluorophores with a higher energy, and therefore give us access to a wider range of the visible light spectrum. And something similar is happening in fluorescent lights, except that the colors that you see is actually coming from the luminescence of mercury, rather than the luminescence of the noble gas. Or the mercury exciting the phosphor in the tube, rather than the noble gas exciting the phosphor in the tube. We're just using the noble gas in this case because it's inert, so we can use it as a kind of filler, and we can ionize it. So you can ionize all sorts of different molecules, but it's nice to ionize a noble gas because, well, it's not going to like react and stuff. It'll just ionize. And so that makes it really useful. So you can have a tube filled with mostly argon and then some mercury in there to provide that initial light that's going to excite the molecules, the phosphor molecules in the tube wall that can then give off light. So this is where you get fluorescent lights. Okay, so that's the basics of neon and like neon lights, and hope that helped.